Hello, welcome to our talk, Attacking the Linux Kernel, Exploit Engineering. So just a quick introduction to us. We're basically the exploit development group at NCC. So my team is responsible for developing exploits used for consultants and engagements to help them achieve their objectives. We're also doing a lot of public research, publications and security research, and doing competitions like Pwn to Own and just general hacking competitions. So there's three of us. It's myself, Cedric, Halbronn, and Aaron, who's not here. So the aim of this talk, it's not just about one specific kernel vulnerability. We want to talk more about the processes and tooling and techniques and so on around developing a Linux kernel exploit. We don't just want to deep dive into one specific bug, but we are going to give examples, practical examples from the bugs which we found. We're going to talk about the challenges going beyond a proof of concept exploit, because proof of concept exploits maybe only work for one system and one target, but we need something which is scalable across lots of different environments. And then finally, we're going to release our tools, libslub, which is used for Linux kernel slub allocator analysis and understanding. So the talk is going to be structured like this. We're going to first talk about the vulnerabilities which we found, how we found the vulnerabilities, and how we triaged them. Then we're going to talk, Cedric's going to talk about the one specific vulnerability which we found, so we can give practical examples of the techniques and tooling. The tools we developed, and then finally reliability and scalability, because reliability and scalability is an important part of exploit development, which people don't really talk about that much. So the vulnerability identification, what we did this time around was, well, this is how we went about finding vulnerabilities within the Linux kernel. We were taking the approach that probably the core operating system functionality, things like the scheduler, the interrupts, the memory mapping subsystems and things like that, they're probably less interesting to us to find bugs. But things like the file system, the networking stack, the socket layer, are all attack surfaces which are exposed from a Linux privilege escalation perspective. And things like new components as well, like IOU ring, it's been introduced into the kernel relatively recently, and is subject to quite a lot of changes. And in the past, we've had things like BPF, because there's a BPF packet filtering interpreter within the kernel. That was obviously an interesting thing to look at. But actually these days, BPF isn't that interesting because, well, at least in Ubuntu, which we were focusing on, unprivileged BPF is disabled. So where do you look? Well, Google have done a really good thing with their KCTF project. So if you're not aware of KCTF, it's a Kubernetes CTF challenge where people have to break outside of the Kubernetes containers and the pods to gain code execution within the node and obtain a flag. So typically this is done using Linux kernel privesks. So if you look at the vulnerabilities which have actually been practically exploited in KCTF, you can see from this list there's there's a bunch of different examples, but things like C group, the net packet subsystem, IOU ring, as we were saying, there's been a lot of practical exploits within IOU ring because because that subsystem was subject to change quite a lot. But yeah, Google have basically came up with these recipes, and these are recipes which are used for exploit development. So essentially the bug classes, the primitives which go into developing the exploit, and the capabilities which are required to exploit these bugs. So one area which we looked at one area which we were interested in investigating was this user namespaces. So if you're not familiar with user namespaces in Linux, it's a way of providing segregation and grouping of resources so they're only accessible within that namespace. but and it's the way which containerization is like the primitives in the kernel which containerization is built on. So things like you have IPC namespaces, mount namespaces, network namespaces. But it's interesting from an attacker perspective because these namespaces, while they are there to provide isolation and grouping of resources, they actually expose more kernel attack surface to a process which is executing within a namespace. So on Ubuntu as well, they've got this unprivileged user namespace is enabled. So an unprivileged user can create these namespaces, and processes can gain these capabilities which they wouldn't particularly be able to have. Well, they wouldn't be able to have as unprivileged if they're outside of the namespace, but within the container, they can actually hold their capabilities. So if we look at the network namespace to start off with, then basically there's we started doing a code review of the different areas which are exposed within the network namespace, and this basically gives you the capabilities to use things like the net filter subsystem, Open vSwitch, and WireGuard. There's also a bunch of like different networking devices which are exposed, and we could find bugs within the within these networking devices and different interfaces which are supported and can be instantiated within the network namespace. We've also got this notion of a mount namespace. So a mount namespace allows file systems to be mounted within a user mount namespace. So typically, an unprivileged user wouldn't be able to mount file systems, but within a mount namespace, they are able to mount certain file systems. And a previous year's pwn2own bug, which was found by Synactive, a use after free in the shiftfs file system, was used for pwn2own. So we did a code review of all the different file systems which are accessible within the mount namespace as well. So we took all this information when we were doing this code review, and we fed this into developing our internal version of syscaller. We forked syscaller, and we basically extended the grammars for syscaller, and we made sure that we were focusing on fuzzing of the subsystems which were exposed within Ubuntu, and because when Google are fuzzing at scale, they're essentially fuzzing on the master branch. They're fuzzing quite wide, but they're not fuzzing like distro-specific functionality. So things like shiftfs isn't covered. We took the coverage maps, so we were looking at syscaller to basically identify where gaps were in the coverage. We looked at change logs. We worked our way backwards through the kernel change logs from the newer versions to the older versions, and added and extended the grammars for this. Zeri's written two really good blog articles about how you extend syscall grammars, because I don't have time to go into it here, but he wrote some things about external network fuzzing and USB fuzzing, extending the grammars for this. Then we also did a targeted functionality fuzzing. So with all this information which we gathered, we decided to focus on a number of areas. So we focused on the net filter subsystem because net filter was, it wasn't previously exposed. I mean, it's not exposed to an unprivileged user, but inside a network namespace it is. We focused on the packet scheduler because when we were reviewing the code, it looked like it wasn't particularly as high a quality code as it could be. And we focused on OVS, Open vSwitch, because there were literally no public grammars for Open vSwitch. So then we took a Threadripper box with 64 cores. We could have used some cloud-based fuzzing for this, and we basically we threw this again with 28 VMs for like a couple of weeks at a time, just focusing down on these specific areas of functionality rather than going wide across the kernel. And we tried to do things like porting the ASM1 parser from kernel space. We moved that back from kernel space into userland so we could fuzz that with libfuzzer as well. And I believe Amat's talking about ASN1 and like possible weaknesses in that later on as well. So I'm now going to talk about the vulnerability triage and what we actually found from this. So to triage these fuzzed vulnerabilities, we basically, I mean, it's quite time consuming. We didn't really have an automated way of triaging these issues. Like on Windows, you have things like bang exploitable, it gives you kind of an indication, but we were basically just relying on our experience and knowledge of what could be an interesting crash. But obviously focusing on things like which triggered KASAN, so issues which were very likely to be memory safety violations. And then we basically filed these bugs into a bug tracker. So because we had quite a few crashes, we'd file anything looking interesting, and then we could go back and and investigate these crashes in a lot more detail like later. We wrote some automation as well for doing automating triage of Syzbot. So Syzbot is Syzbot's Google's dashboard for syscaller, and it allows them to manage different syscaller nodes and provide a dashboard with all the crashes in. It also does things like emailing developers when a bug is found, and then they can investigate the crash and triage it and so on. But we noticed that the Syzbot bugs, like they're not always actioned. Like maybe the developers are too busy, maybe they don't realize that it's like a security relevant issue, or it just gets put on in the backlog and never looked at. So we started looking through those, and this gives like a good indication of areas to look at as well, because we can see from Google fuzzing at scale and us fuzzing as well, what the kind of vulnerable areas could be due to like bug clustering. So this is useful for KCDF. I think this is one of the reasons Google possibly running KCDF to incentivize people looking at these crashes and to reduce the amount of NDAs just sitting there in the Syzbot dashboards. And also possibly prone to own as well, because I mean, are these an O-Day? It's debatable, but if the developers aren't actioning them, if the developers aren't aware of them, then maybe it is an O-Day. So we wrote some Python scripts to basically pull down the different crashes, do filtering of looking for specific types of bug class. So use after freeze, out of bounds writes, the kind of things which we know which are very likely to be exploitable. And then when we ran them against Ubuntu as well, like a KASAN build of Ubuntu to triage whether it affects them or not. So what vulnerabilities did we actually find? Well, as I was saying, we found it through Syscaller, and in this run we basically found 3 vulnerabilities. We found 2 vulnerabilities which were with reproducible test cases, with actual tests which we could run and reproduce the issue. So one was a heap overflow in legacy parse parameters, which we wrote an exploit for. But another team actually they exploited this issue for KCTF and beat us to that one. And then we also found an out of bounds write in WatchGuard subsystem, which I think John Horn also found, and we exploited that as far as getting a KSLR leak. But the third one we're going to talk about today is one of the issues which wasn't reproducible. Like there was no test case to actually reproduce this from Syscaller. And we had to manually triage this to determine the root cause of the issue. And this meant that we didn't get duped by any of the teams as well. So this issue, it exhibited itself as in the KSAN output. It was a use after free and NF tables bind set. It was a use after free write, a write of 8 bytes to the freed chunk. And so triaging it, we started off by looking at the alloc to see where and we could see that it was calling NF tables new sets to create a new set, and then it was allocating an expression, and then free to free the expression. And then the use after free part, we could see it was doing it was calling NF tables bind set, and essentially binding, it was doing some linked list operation, list add tail RCU to add something to the tail of a linked list. So we were thinking, yeah, this is possibly like a dangling pointer within the list, the sets. So so how do we triage this one then? There's no manual way of doing this. I mean, there's no automated way of doing this. Again, we had to do manual analysis. It just required a lot of time, understanding the source code, and looking at things like where the allocation happens, where the free happens, and where the user free part occurs, and then trying to piece together, like build that mental model of actually what the bug could be, then writing some like test cases to try re-trigger the bug, and finally we managed to reproduce the bug just from source code analysis and infer the vulnerability side effects from this. So an interesting thing about this bug is that Syzbot did actually find this one as well, and it was sitting within the dashboard since November 2021. But no, I didn't see this, and I don't think many people are aware of this. Zhukov, who was the guy who was maintainer of the Syscholar project, he pointed this out after we released our blog post on exploiting this issue. But it just goes to show, like, there's a lot of vendors just sitting around in the thing. So I'm now going to hand over to Cedric to talk about the bug itself and the techniques.
Okay, so the idea of talking about this vulnerability is just taking it as an example, so we can talk about everything else. But so we're not going to go into like huge details, and especially because if you are interested in this kind of really huge detail, we've published a really long blog post. Has been a presentation, and also other company like Theory actually did their own exploitation method, so you have lots of content. But basically, the idea is we are in an NF table, and there are lots of different objects, but the only two we are interested in are a set and an expression. And the idea is that we are only interested in this kind of scenario where we trigger the vulnerability. The idea is we have this set object, okay? You don't even need to understand what they are, but basically this set object has a linked list, which is called bindings, and so it's a linked list of expressions, okay? So at some point you can have a set that has a linked list of expression. And somehow we trigger the bug, and what happens is we have, like Alex was saying, we have a dangling pointer to a free chunk, and it happens to be a previously allocated expression, okay? And this pointer to this dangling pointer is inside this linked list. So it can be either from the set itself, so the beginning of the linked list, or from another expression in the linked list. And basically, like Alex was saying, the use after free occurs when we try to insert or remove another expression from the linked list. Because the operation to insert or remove an element, if you're familiar with a linked list, is basically to update pointers, and so it's going to basically write a pointer into an adjacent chunk. But basically, the other scenario we can think of is, there is already an expression in the linked list. And so in this case, the dangling pointer is not from the actual set itself, but it will be actually from another expression. And so we have this dangling pointer to a free chunk inside an expression. And so what we can do is we can remove the expression because we created all these objects. And when we remove this expression, it's going to actually write the address of the previous element in the linked list, which in this case is the address of a set, into a free chunk. So obviously, writing a pointer into a free chunk is not useful, but at least we know what the primitive gives us. If you want to understand the rest of this presentation, this slide is basically telling us the bug gives us a way to write a pointer into some free chunk at the moment, and it could be either the address inside a set or inside an expression. And so, sure, as I said, overwriting a free chunk is useless, so we want to be able to replace that free chunk with some other object we control, and then we trigger the limited write primitive. We overwrite the pointer inside that chunk, which is not free anymore, and we corrupt a potential object. And so here, it's basically the same kind of thing that you have to do. Is basically either you use that to write a pointer that you leak back to userland, or you corrupt something else undetermined for now, which is going to be another in another object, and you are trying to improve your privileges to something bigger than just a write primitive of a pointer. And so, yeah, we're going to use both. This is kind of the summary of the exploits from the high-level perspective, and so it's going to basically be useful to explain all the different concepts in the rest of the presentation. But basically, from a high-level perspective, we use 4 use after frees, which can be a lot. But basically, the limited use after free, the one I've just presented, we use it twice. Once to overwrite some object and then leak it back to userland, so we can leak some objects from in the kernel. Another one to actually get a better primitive. So in our case, we're going to corrupt a pointer, and then we're going to be able to free a legitimate set. And then once we have done that, we can replace the set and just use after free the set as many times as we want, and just interact with the set from userland and maybe abuse the fact that we control the fields of the set structure. And so in our case, we just needed it to do the use after free on the sets twice, once to bypass kernel ASLR and kernel pointers, and another one to kick off a grub gadget in order to overwrite the modprop path and then get a root shell. So yeah, 4 use after frees. So we had a couple of options for the demo. Either we do it live, or it can fail. Either we do it as a video, it can fail, or we do it static. So hopefully it doesn't fail. But basically, the idea is I want you to see that there are 4 stages. The first stage is we do the limited use after free to leak a pointer, which is the address of a set. We have 2 sets, set 1 and set 2, so we leak the address of set 1. In stage 2, we use a second set 2, in order to corrupt a pointer into a C group object. And then once we've done that, we can basically use after free a set because we control the fields, and we use it once to bypass kernel ASLR, and then on stage 4, we use it to kick off the grub gadget. And yeah, we are brutes. Okay. So now we know an example of vulnerability we have exploited. Let's talk about the general things we have to deal with for any bug. In this case, we want to be able to spray small objects to replace the expression. We want to be able to replace large objects because set in the use after frees 3 and 4 are large objects, so we need to control the content. And also, we're going to show how we can abuse the set structure, because in our case, we chose to use after free a set as a good primitive because, as we can see, it's going to be quite powerful. So I'm just going to start from the end, which is basically assuming we can corrupt a set. And so in this image, we have 2 sets, set 1 and set 2. But actually, set 2 has been corrupted. We were able to free it with our primitive and then replace all its fields. So we called it fake set because it's a fake set content. But actually, it's a real set from the operating system point of view, so we can interact with it. It's just we control the fields. And so what can we do with that? Basically, the most important fields are the UData and UDlength. Basically, in a set, you can actually, at creation time, you can actually control some data that's going to be stored inside the set. So it's going to be appended after the actual set structure. And so it's basically user supply data, and you can not only write them at creation time, but you can also read them back, which is going to be quite handy. The other thing is if we can actually leak. So what we do is basically we corrupt, assuming we have leaked the address of set 1 already, which we'll do in phase 1, we can actually corrupt UData and UDlength to point to set 1 because we know this address. And then what we can do is we can leak all the content of set 1, which is the first thing, but we can also potentially leak the adjacent chunks as well because we can set UDlength to be not only the size of set 1, but also adjacent chunks. So that's pretty cool. But we have a few constraints. For example, the name of this fake set needs to be a valid kernel pointer to a string, because in order to interact with it from userland, it needs to be valid. So, but it's not a problem because we can preliminary allocate, when we set 1, we can store a fake name into its user data, and once we have leaked the address of set 1 anyway that we need for writing new data, we can just set the name to the right offset. The other thing we can do from leaking set 1 is we can leak a pointer into the list a linked list, which is at the first element. It's a list of sets that are associated with the same table. So if we have set1 and set2 into the same linked list, we can just leak the address of set2, and then it gives us more power. And the last thing is the set structure actually has a pointer to a function table called ops, which we can potentially use for kicking off a ROP chain, because there is no CFI. Okay, so how do we actually overwrite a set? I said it's a large structure, so for user after 3 and 4, we need large objects. But we also want other objects that are large that will be on the same slab cache in order to bypass kernel ASLR that would actually contain pointers to the kernel. So this table, I'm not going to go over all the techniques because there have been many exposed, but it's just to show that basically techniques evolve over time, and vulnerabilities take always the same technique until they are dead. And that, for instance, I'm showing that message used to be a technique that I've been using many times, but it stopped working from the exploitation point of view because the object ended up moving to a different cache that is not useful anymore in the general cache, because they are in the kmalloc ng instead of kmalloc caches. Another example is user4d, where by default in some distribution, they will basically disable the fact that you can actually interact with user4d from an unprivileged normal user. I mean, I'm not listing them all. There are many other techniques, but the idea is, for instance, here in our case, we can actually use setx attribute in order to control the data of allocation of large size in the kernel, because all we need to do is create unprivileged user and mount namespaces. So that works to replace the set content. And then we need specific object that contain kernel pointers, and we can use tty struct object because they contain a pointer to the kernel. However, they are in the kmalloc 1K, and our sets initially are in the kmalloc 512, but all we need is just to add data into the actual set to increase the size, so we end up being on the right set, on the right cache. Okay, one interesting thing about this leak we've used, which could be applied to any other leak technique, is basically when we spray tty struct and we allocate the set, the idea is we want the set to be before other tty struct, but what could happen, like in the image, is that the set is actually at the end of a slab. And so if we try to leak the content of set1 and try to leak the content after set1, we're not going to leak anything because it's going to be not a slab being allocated yet. And so it's going to be annoying because it means we can't bypass, we can't get this address which we need in the first place. But the interesting thing is that we actually leak the address of set1 in the first use after 3. So from our perspective, what we can do is we can just check the last few bytes of the address of the set we've leaked, and we can detect if it's actually at the end of a slab, and you just do some math depending on how many objects there is in the slab and what is the size of an object, and you can just detect that, which is quite handy. And it's an important reliability aspect because it means we only need to trigger one use after 3, and then we can just restart the exploit from scratch instead of triggering 4 use after 3s and detecting that afterwards. So the other thing we need is we need to be able to spray small objects in order to initially replace the expression for the limited use after 3 for use after 3 1 and 2. And in this case, what matters is very specific to our vulnerability, which is that the write primitive we have is dictated by the offset or where bindings, the field name bindings is in the expression structure. And so, for instance, it's going to be the object is going to be into kmalloc 96, and for instance, the prev field will be at offset 72. And so, again, I'm not listing all the objects, but the idea is, for instance, we can use the user key payload structure, which has been abused many times. And the idea is it's usable because this structure can have you can change the size by appending different data to the object, but it has a specific header of 24 bytes. So if the offset we wanted to write was in the 24 bytes, it would be useless, but because it's in the actual data, like payload of the structure, we can overwrite this payload, and then we can read it back from userland to userland. So it allows us to leak the kernel pointer initially for set1. And the other thing we need is we need to corrupt, to get a better primitive than this limited use after free. So we need to find an object with an interesting pointer at offset, for example, 72, that we can corrupt and then abuse somehow. So this is kind of very specific to this bug. So we need to find new things, right? We can't find it. So here, CodeQL is very good for this kind of thing. If you have to deal with this kind of challenge, the idea is you can ask CodeQL to say, I want to find objects allocated with kmalloc, like structures allocated with kmalloc in the kmalloc family, and that allocate into a chunk between, for instance, 64 and 96 bytes. And I want that at offset 72, there is a pointer. So obviously, you may have lots of false positive things you can't allocate from userland or whatever. But for instance, we found this C group structure that is allocated on kmalloc 96, and that has a character pointer called release agent at offset 72. So that matched the first thing we need. But we also need to be able to allocate it from userland. And so what we do basically is we check it's, you can actually allocate it from userland with fsopen. We can free it from userland with close. And by closing the C group, what's going to happen, as you can imagine, it's going to free all the element of the object, and it's going to free the release agent. So it gives us basically a way to free a pointer. So here, going back to the scenario, we are able to free a pointer. And so in our case, it means we are able to free a pointer to bindings, like the address of bindings into either an expression on a set. And so here, basically, what matters is that it's going to actually take this address and it's going to create a free chunk that's going to overlap. So in the case of the expression, because the bindings element is at the end of the actual object, it's going to actually create a free chunk and overlapping a lot to the adjacent chunk, which is not ideal because we don't know what's behind, and we're not going to control, if we replace the expression, we're not going to control the actual object. But in the case of the set, it's only at offset 16, so 10 hex. And the set expression we've seen is a really big structure, so we're going to be able to corrupt most of the fields, abuse it like I've explained before, and we're not going to corrupt a lot in the adjacent chunk. So that's good. So we're going to focus on the set. So just going back to the scenario initially where we trigger the bug, we have a dangling pointer to a free chunk. In the expression, what we do is we replace the free chunk with a C group, the object we found with CodeQL. This object has a release agent pointer at the right offset. Now we free the expression. It's going to actually corrupt the release agent with the address of the bindings, in our case, the set2 bindings address. And now what we can do is we just free the C group, and it's going to actually free set2. And now we can replace set2 and have arbitrary content and control its fields and abuse the fact that it's control set that we can interact with it from username. So one thing to take into account when we trigger use after free is that the time you need to actually, between the free and the capability to replace the chunk before something else on the system actually replace the chunk. And it's something you have to deal with all the time with use after free vulnerabilities. And so in our case, the interesting thing is that we had different environments, QEMU, VMware, whatever. And basically, one of us was using VMware, and it kept crashing, but not on the other one in QEMU. And it turned out it was because of the combination of a debug message being printed from username that would trigger handling by the VMware graphic driver. You can see VMWGFX. And the crash happens because the chunk is overwritten, like the chunk handled by VMware graphic driver is overwritten with our pointer, and everything, it doesn't like it. Okay, so now let's move to debugging tools. So we want to talk about two things. One aspect, which is how to use the debugger to help us assisting us with debugging different use after frees, because we have 4 of them. And then talking about libslub, like a heap analysis tool we wrote. So the thing about, we have 4 use after frees. So if we have to debug use after frees 3 and 4, and at first when we poke the exploit, use after free 1 and 2 are not very reliable. It can be annoying to just having to execute the exploits, and it fails on use after free 1, and you want to work on use after free 3 or 4. So basically the thing you do is you just write a GDB script that's going to log the address of set1 and set2 at set creation with the nf table new set function. And then later, when you try to interact, for instance, with set2, we just assume we corrupted set2 by just pointing the udata pointer to set1, UD length to be a bit large size, more than set1, and then timeout to be a value that you can check from userland and say, okay, we assume now we corrupted the set and we just work on the rest and make sure it works. And it can be very handy, especially when we are several people working on the same thing. We can work on different aspects. And then the same thing for if you want to simulate all the use after freeze, you just want to kick off the ROP chain and just debug the ROP chain to make sure your understanding is correct. Okay, so let's talk about libslub. So libslub is a Python library we wrote. It's a GDB Python library. And the idea is we want to be analyzing the slab management structures as well as the object allocation. It's currently designed for GDB, but if you want to adapt it for LLDB, for instance, it's really easy to do. It's open source. We've just released it today on GitHub. And the idea is it has to be very customizable, which is that it's going to print as much as you want if you want to parse everything. But also you are able to pass certain flags and then it just prints only certain parts. And we want it to be fast, and we cache not only the slab structures and object addresses. So if you're in a breakpoint, you can you don't have to always parse all the structures all the time, and it's fast. There is another plugin called slabdbg, which is kind of similar, but we have different ways of doing things. So one thing I want to say that by developing this plugin, we learned a lot about this slab internal, and it's important, we think, from a long-term perspective, where sure, for this vulnerability, we had certain challenges to solve, but for another vulnerability you've seen this morning, it's always the same thing, slab cache, you have to deal with for different bugs. And so the slab allocator is the generic term. You have several implementation into the Linux kernel, slab, but basically slab is the latest one on the latest desktop kernel implementation. So we're just going to talk about this slab implementation. And so basically if you're not familiar with kernel heap, I know we've talked about it already today, but because we're going to talk about the plugin, I just want to make sure everyone is on the same page. We have the concept of cache that contains slabs, and then slabs contain basically object in memory regions. And so the cache is this concept of object all of the same type kind of thing. So kmalloc 1K will be object of size 1K, 1024 bytes. And so this cache will contain several slabs, and you have different slabs that you have to deal with. You have the main slab, what we call the main slab, which is basically the current slab that is used for the allocation. And then you have this concept of partial slab that contain allocated object, but also not allocated object. And the idea is when the main slab becomes full, because there is no room anymore, and we can't allocate new objects from this slab, partial slabs can become the new main slab. And you have this concept of full slab, which is basically not used at all because they are full. They contain only allocated object. And so, yeah, it was mentioned this morning, but main slab and partial slabs are associated with a CPU core, whereas a full slab is not. So it's important to understand that sometimes if you are in a multi-CPU scenario. And then the slab is composed of what we call memory pages, which the number of memory pages for a given slab depends on the object size and so on. So, okay, so going into libslub. So this is kind of the output you would get from libslub. All the commands start with SB, like slub, and then you can do SB help to get all the commands. And the idea is you would be able to list all the slab with SB list, and then you would be able to filter with using -k, for instance, to just filter all the kmalloc caches just because they are very interesting from an exploitation point of view, and you can filter with specific patterns. Then the SB cache is like the generic, like overwhelming command that's going to print the contents by passing all the structures. So we do print like all the different structures. You don't really need to understand them, but if you want to really understand the internal, it's useful. But basically, the idea is what is useful here is that we have you can see the free list, which is a pointer to the first element in the list, and then we print that we have 5 elements, so we already passed the free list to print it. And then we see the region, so we see the first object will be at address ending with 1600 at the bottom, and it has 16 elements. And then obviously we can print more stuff by having more verbosity just to print the region, to print the element of the free list, or also to hide the structures if we're not interested in these. So one thing that is useful to know about the slabs as well is you have this concept of lockless free list and regular free list, which people don't always talk about. But basically, each CPU, as I said, has a dedicated main slab, but the main slab actually has two free lists, which, if you think about it, makes sense. But the idea is you have, because it's associated with, because the main slab is associated with one CPU, and if several CPUs were actually freeing object or allocated object, you don't want them to mess up with the same free list at the same time, or you're within the lock, and then it would be inefficient. And so the main slab that is associated with the CPU, this particular CPU will have a dedicated free list, which is called lockless free list, and it's going to use this free list for allocating and freeing object. And all the other CPUs will never use this main slab for allocation, but if they free a chunk that happen to be from this main slab, they will be put into another free list. So there is no problem of lock. There is no problem of racing. And obviously, this other free list, you need a locking. So in this case, for instance, we just showed the output by just printing the lockless free list and the regular free list without all the other things. The other thing I want to talk about is the fact that sometimes really understanding the internals helps with improving user after free scenarios. Because if you think about the fact that I've just explained that the main cache is associated with one CPU, if you think about a scenario where it only has one free chunk remaining in the main slab, and the main slab becomes full, suddenly, basically, what's going to happen is the main slab is going to change. And so if you're in a scenario where you're trying to trigger use after free and you want to replace a chunk, it's adding another layer where it's going to make it less reliable because the main slab changes completely. Even if you have a free chunk that gets replaced by something else that gets refreed again and you want to replace it again by your allocation, it's never going to happen because the main slab completely changed and there is no way it's going to work. So the idea is we want to defragment the cache. The way we do that, we allocate lots of objects. For example, here we just use C group, but you can use any object you want. And then you just free the number of elements into that you know they're going to be into the slab, and you increase the likelihood that there are going to be lots of free chunk into the lockless free list and that the main slab will remain the same during your operation. The other thing we wanted to support in the tool is a way to execute commands for all of the objects of the system. And so the idea is we can execute a GDB command for all of the objects. And so we can, again, use the SB cache command, but any command will work. And for instance, in this scenario, we said, print the object as if it was a TTY struct and print the ops field. And so we can see that some of them have the PTY Unix 98 ops field, which indicate that they were indeed TTI structure. And so it's useful if you want to do something and you crash, and after the fact you want to parse the layout and see what is in memory. So another thing we wanted to support is wanted to support the fact that we wanted to be able to tag objects to say they are of a certain type. So if you think about having a breakpoint on, for example, the allocation of TTY structure structures, and we can just say add that these objects are we tag them as being TTY, and then later when we use any of the commands, and we want to show the tag, we'll be able to see where they are in memory, which can be quite handy. Okay, the last thing we wanted to be able to do is we wanted to be able to track full slabs, and the slab allocator doesn't need to track full slab because they're not going to be used by a new allocation, so they don't only track partial slab and main slab. But basically, from an exploitation point of view, it's very useful to be able to track full slab because usually we spray objects, we want an object between other objects, and then it becomes full because we want to make it reliable, but then we can't find it easily. So there are two methods to actually track full slabs that we found. Basically, the first one is to actually set breakpoints on slab functions and just tracking when the slabs are allocated or freed. But the problem is this triggers all the time, and GDB sometimes crashes. So this is kind of annoying sometimes to deal with this problem. The other method is to just log the object addresses and the associated slab by setting a breakpoint on only the object we are interested in. The advantage is it doesn't crash. The drawback is it's not going to log all the full slab, but generally all you're interested in is the object you're dealing with anyway, so that works. And so, for instance, here we can see that we tagged the set and the TTY, and we see that our set ended up being in a good layout before TTY. The last thing it helps with is the scenario where we trigger use after free, and when we reuse the chunk, we realize that the object hasn't been replaced like we wanted. And so basically what we want is, for instance, to spray key to replace the freed expression. It doesn't work, and we use libslub to find why. So, for instance, here we are allocating. We had allocated an expression at offset AA that ends with offset AAE0. It was freed, so we can see with libslub it was added to the lockless free list, obviously at the end of the list on top. And then later, when we allocate the key, we realize it's A7E0. So it's actually we're missing 6 chunks, which is really bad because it means we'll never have good reliability. And so here the idea is we can basically know the address of the previous element in the linked list, and we can investigate what are these objects and try to find why and how to improve the reliability.
Thanks. So moving more into reliability and scalability. So this is really important for us because we need to increase the UAF success rate. We also need to backpod the exploit to older versions, and we're going to talk about some tooling which we've developed to actually do this. So as Cedric was saying, we exploited 4 different use after frees. That, 4 of the same use after free, but multiple times. And that can introduce system like instability because we need to reallocate this freed chunk with some controlled data before the system can actually before some system allocation can occur and take that and take the freed chunk. So Kyle from ASU, he wrote a really great research paper, and which came up with this concept of context conservation. I'd not heard of this before, but essentially it was a way he developed where basically it's a way of reducing the likelihood of a context switch occurring, and if you can make it so that that your exploit frees and reallocations occur within a time slice, then it's more likely that that the system isn't going to take the freed chunk before you have a chance to reallocate it. So he does this by injecting a stub into the process, and to measure when a fresh time slice can be allocated, and then you can perform the exploit critical functions within that time slice. We also did some things like we basically reduced the amount of code between the free and the allocation, because if we've got things like doing things like inlining functions, it can reduce the amount, potentially make it so that there's less likely for a context switch to occur, and reducing unwanted debug code as well. So if there's like a debug statement in, maybe that can cause unwanted memory allocations to occur. We also implemented CPU pinning as well, which so we had to pin our exploit when we trigger the bug and the reallocation to happen on the same CPU cores as well. So the same slab cache is used, and so overall we actually got our exploit down to be about 100% success rate overall. We got it we had to sometimes trigger the UAFs multiple times, but we got to the point where we weren't causing any system instability and being able to not panic the systems. So while we were also trying to test our exploit at the same time. After we'd done this, we were testing our exploit. So the Linux kernel developers, they knew which commit the vulnerability was introduced in, and they said it went back as far as the Linux kernel 4.9, but we were a bit unsure about that because the code had changed quite a lot between 4.9 and the latest master. So we basically used syscall to create image again, just a quick way to spin up a KA-SAN image to test the bug and to test our trigger to see if we could trigger the bug and confirm if it was there or not. But we actually realized when we went back to 5.10 that the code had changed in NetFilter, but our vulnerability was still there. It's just our exploit wouldn't trigger the actual vulnerable code path, and we need modified to trigger it. And we went back as far as 5.6, and then we were like, okay, well, NFT set alloc expression is missing, so it's unlikely that we can exploit it in this. And we worked out, and we ironed out some problems with our exploit, which we were going to give to consultants. So things like if it's missing fuse support, then we won't be able to use our techniques. And obviously, if it's missing unprivileged namespaces as well, then we won't be able to trigger our bug. So the Linux developers, they were backporting their fix to the older versions at the same time as we were backporting our exploit. They were, and they went back and ported the fix to 4.9. And we were manually, but while we were doing this, we were manually hunting all the offsets, which is pretty tedious, like going through, like looking in IDA or looking and to work out what symbol offsets and struct offsets and so on, which we need. But just like a small diversion, it's interesting to look at the disclosure timeline as well from an attacker perspective. It's quite a complex process, patching a Linux kernel bug. Like, it gets pushed, this one got committed to the netdev tree, then it got merged in the BPF tree, then it got merged in the Linus's tree, and then it finally was like in the Linux mainline. Then all of the actual downstream distributions need to pick up the fixes. The fixes needed backported, as I said, but then the fixes initially, they wouldn't apply because the code had changed, so the developers had to rewrite some of the fixes to actually apply it correctly. And then, finally gets pushed out to the consumer. And for some reason, Red Hat Enterprise Linux was like the last one to patch, like a commercial one. But Ubuntu and Fedora patched relatively quickly. Yeah, so anyway, that was a bit tedious, like manually doing stuff. So we need to improve this. So we developed a set of tools for automation and creation of testing environments. Because the software and kernel versions and so on which are installed in target environments can vary substantially. And because memory corruption exploits that can often contain like static offsets, then we basically had to automate this. So we defined this, we created a tool called target mob and defined a vocabulary. This is basically allowing us to do automation of QEMU, Docker. We can do different Linux distributions, the release, the architecture, so all the different architectures which QEMU support. And we can say our target environment needs to have these specific packages installed or versions of the Linux kernel. So we split our architecture for this into two different components. We have the mining pipeline, which is essentially like static binary work, so it crawls packages, extracts offsets and symbols, and so on. And then we have the testing pipeline, which actually builds the environments, tests our exploit in the environments, and gives us results. So the mining pipeline, this looks like this. We basically define a project configuration, which is like the packages which we want installed in the environment. Then we gather the package information, scrape the package information from the APIs, if they're provided by the distribution. And then we can do things like generating ROP gadgets, structure sizes, and so on for the different kernel versions. And then finally, our exploit-specific project extraction. So the project extraction, for each of our exploits, we write a JSON file, which defines the offsets which we're interested in. So the symbol offsets, the structure offsets, which we care about. And then based on this, we can generate like all the offsets for the different releases of the kernel, which we care about, and integrate that into our exploit. So as you can see, here's the symbol offsets and the structure offsets. Then from the testing perspective, we build the image. So we build our QEMU image, we run the image, and we deploy our exploit to the image. We've developed this notion of exploit profilers, where we execute our exploit underneath with a profiler and then analyze the results. So this is good because we can basically say, okay, we need to build all the Linux 5.13.0 and like star for wildcard, and then we can build all of the 5.13.0 environments. So here is just an example of 30 different buildable environments which we've got with the different kernel versions in. Then our profilers, we implement an exploit profiler, and that basically profiles the execution of the exploit, determines whether the exploit is successful or not. If the exploit isn't successful, we can gather heuristics and like heap information or figure out why or stack traces and so on, and figure out why our exploits has failed, and help us analyze it. But to do this, we need to define like a standardized interface for all our exploits to follow to actually to work with this. And then finally, this is just a demonstration of the kernel profiler running. So we're running this profiler against 5.13.0 and 1919 environment. This will basically download and install the desired kernel, reboot into the image, copy the exploit up, execute the exploit, gather results, and determine if it's successful or not. And that's an example of the exploit profiler running, just showing like ID first as a low privilege user, executing the exploit, which we called settler, and giving us a return code of 100, which is exploit successful. And then we can scale this up across lots of different target environments. So in conclusion, I just wanted to say there's a lot more to exploit writing than just proof of concepts, like especially if you have to target lots and lots of different environments. And and we think that the tooling and automation is really important, because you want tools which you can reuse, especially if you're developing like lots of say Linux kernel exploits. Then you can build a scalable process for these tools. I would have liked to have talked about defensive thoughts, but it's an offensive security conference, so nobody really cares. But but basically, I think patching alone is not really enough. There's the attack surface of the Linux kernel is pretty huge. The code's changing all the time. You can see there's endays and things just already sitting out in the public, which people can write exploits for. I think the only way really is to do attack surface reduction, and to reduce the attack surfaces which an attacker has to look at. So things like Firecracker, gvisor, NSJail, and things like that will be good research areas in future, because they are going to prevent a lot of the Linux kernel exploits in their current state as they are, without specific like Firecracker bugs or gvisor bugs. So so we're going to release the code, libslub. It's now available on GitHub, so you can clone that now. We created an exploit mitigation repository, and where we're trying to track different exploit mitigations across the different platforms. It would be good to get more contributions there, because crowdsourcing the exploit mitigations, because there's a lot of exploit mitigations out there. And we may release target mob as well at a later stage if there's interest in us releasing these tools as well. So yeah, thank you very much.